Sí, el vídeo, ¿eh? Vamos a ver.
I'm doing ads for, you know these brands? I'm doing that for these brands. Yo tengo aquí.
Que sí, con tecnología de la NASA.
Yo ya yesterday
There were instructions.
Yesterday was too cold, but I forgot. Really cool.
Què passa aquí? El document 3 és l'antic, encara. Això, si baixa't al 4 i et penjo el 3 al xat. Ara l'estan penjant, però no és automàtic.
M'acaba la bateria. Vamos a conectar y digo cuarto.
Sí. Ayer, bueno, no, estuve hasta las 6:30. No sé, o sea, me quedé atrapado en la simulación. Quería echar unos casos de Mare Nostrum. Mare Nostrum siempre te has hablado.
Mare Nostrum, ¿puedes entrar cuando hasta ahí estás?
Tienes que estar en un proyecto.
Sí, pero una vez estás en el proyecto, tienes que pedir.
Tienes que pedir, hay formas de pedir, pero cuando normalmente...
Archivos borrar todo, creo que eso es como borrar todo.
En el 4, en el 3, que
A ver, el punto.
pedir una situación normal, ahorita es probablemente automático. Pero cuando pides de high memory, o sea que quieres un...
A ver, pinta.
Sí que te tarda tal vez.
Yo creo que no me es el primer todo.
Pero en el Mare Nostrum 4 ya no tienes que tardar una media hora o algo así.
Está bien. Si no sé si estaba bien con esto y llevaba 6 horas de la pantalla. Avisar también.
A ver, ¿qué estás jugando?
Esto es como una arteria.
Yo no soy psicólogo, llevo retos
para hacer pruebas. Entra el flujo de sangre por aquí. Y esto es una disección aórtica. Esto es el es la enfermedad que tratamos. La sangre fluye por aquí. Lo que hacemos es poner un parche aquí.
Vale.
Es pues sacar los datos de ese flujo de sangre aquí y utilizarlos como input en un modelo que para mirar la permeabilidad del tejido y si fluye sangre o no a través del tejido. Sería la sangre que pasa a través del tejido. Si la bonaría bien o no, digamos.
Okay, thank you. And you can put.
Y nada, o sea, tenía que durar un segundo, yo podría hacerlo aquí. Además, el ordenador iba a salir.
¿Cuántos elementos?
Tiene 1 millón de nodos.
300 sería, no? Però...
Ahí en la esquina de abajo de la izquierda,
No serà això? No.
5 millones.
5 millones de elementos.
Ara no sé ni on estaven, no?
¿Dónde lo estás poniendo? ¿Cuántos gigas de toma?
O sea,
Com estava?
de
El Windows li has donat?
El problema es que ahí tenemos instaladas una versión más antigua de estas cosas. Y ahora no tenemos.
No, això sembla com per connectar, no? Ah, sí. La d'abans.
La pantalla
Sí, a mi.
normal.
Igualmente, ahí en la universidad, esto tarda
Una portàtil, a veure. Jo crec que això és la connexió que hi ha. És l'HDMI.
se puede mirar de alguna manera.
UPS, sí.
Vale. Utilitzes això. Llavors aquí, com el zoom, ara el que estan veient és allà.
Has posat el xat? Agafem el
Cada vez it's in it to run
Això és a l'estiu.
Fins que compartim pantalla, no? On estava l'escriptor? Què vols fer? Aquí això. I ara, per fer gran petit així, si faig servir això.
Això et marca...
Però no pots escriure. Això és per subratllar. I enrere com es
Ese problema creo que es así. Estas 4 computadoras,
completa. Ya contrastando. Llavors, la Wi-Fi, ara la
hago unas
Sí.
similitudes. Lo que pasa aquí tiene que ver con lo que pasa.
Has obert l'aplicació. I usa això. I ara, que va bé. Ja vist va bé. No van a veure la goma de xocolata. I la goma, farem això. La part de darrere? No, funciona que va de valentar i tal. Però a veure, torna a provar amb la part de davant. Borra amb la part de davant, no borra. No, sí, no borra. En canvi, sí.
Vale, bueno.
Pues estàs en el modo goma i sempre tens llapis i goma. No fa falta que et fiquis. En el modo goma, llavors vaig fent així i esborrar i ja està.
Tenim una càmera i això, Entesin això.
Com he d'això ara?
You know, see, you know, more than enough.
Llavors, no. Llavors has de tenir aquí i...
We actually code in Fortran.
No, hem de tancar-ho, jo crec. Tancar i moure'm. I després, si vull tornar a fer-ho aquí, annotate, i llavors la goma sempre. L'escric aquí i esborro. Per tant, ara fora això, i per un moment, i l'altra cosa és, si vull assenyalar amb el mouse, com ho faig? Vale, si vull assenyalar amb el mouse, com ho faig? Aquí, Sí, si vull només com... Sí, no n'hi ha.
Crec que no.
Si ara està tota l'estona així i de tant en tant...
Pots fer servir l'espai ja.
Okay. But just learn. It's not that you're that.
No, ara s'ha de fer així. Ah, vostès amb això,
We see that window.
No, això pinta igual.
Hey, it's a Windows Surface.
Amb això pots moure el que pintes.
Vale.
Por tu sí,
Ara l'únic que no sé és com fer per...
Has de sortir del mode de pintar.
Una pinta, tancar aquí.
El model s'adequa.
Sí, el que no sé com fer és perquè ells... Em falta ara és saber com assenyalar sense... Bueno, ara aquí sense llavis, però és bastant incòmode.
És el que vull que em detecti.
Vale, va. No fent servir llavis tota l'estona, però hi ha alguna cosa,
No pots dir alguna cosa?
Si no, hauria de pisar-la.
I ja està. Aniré fent això i assenyalant així, ja està. Vale? Vinga, doncs. Ara l'únic que hem de fer és fer el zoom.
Però jo he de buscar...
Espera, crec que has de treure això.
Crec que s'ha
Vale. Good morning a everyone. Llavors,
S'ha de compartir pantalla aquí i gravar, no?
sí. Pantalla.
Toda.
Anem a compartir el grupo, ¿vale?
No sigui o un client que està donant
Está compartiendo pantalla. ¿vale?
Per què vol compartir?
Jo el que faig és analitzo
Això no sé per què ara vol imprimir.
i la gent com i faig línies de referència.
Ara estem compartint pantalla, ara s'ha de gravar, no?
Estan veient això, Estan amb la càmera de darrere.
No, perquè potser estan amb les dues, S'està compartint, S'està compartint, segur. L'únic que tenen les dues opcions. Ara, si no preguntem, is there someone connected? Can see if we are sharing the screen or not? Vale, sí, ho estan compartint. I ara, això s'ha de gravar simplement. Minimitzem.
Has de posar a gravar abans de compartir pantalla. Perquè ara, com que se't tanca el menú i no...
Vale, ho fem així.
Grabar en la nube
Recording in progress.
y ahora compartir pantalla. ¿Ya?
I ara ja està.
Perfecte, Àlex.
Molt bé. Així i així.
No, espera.
Doncs es veu aquí. No, això només ho veu la gent d'aquí.
Ostres.
Crec que no és pantalla, sinó que s'ha de canviar la càmera. S'ha d'agafar la càmera de la tele.
No, perquè llavors només es veurà... Home, també es pot fer compartir la pantalla de la tele.
Sí, si tu vols treballar en aquesta pantalla, o sigui, hem de compartir, hem de fer servir la de la tele.
Ara de compartir. Però llavors no tenen el zoom posat. S'ha de fer més zoom.
No, perquè compartim directament això. Sí, perquè la càmera és la de la tele, jo entenc. Sí, si treballem a la tele, es veia així perquè volíem aquella càmera per veure la pissarra. Però si el que volem és que sigui aquesta, hem d'agafar la pantalla de la tele. Llavors veurem directament aquesta, que no veuran és la classe.
Però què vols compartir la pantalla?
Sí.
Què estaven fent? El problema...
No compartir-la, perquè és canviar la càmera, que jo crec que s'ha de fer.
L'altra opció és que aquesta càmera faci zoom i s'acabi veient això.
Sí, per això no hi havia posat la càmera.
I també estic fent un capnós.
Si compartim pantalla... Vale. Ahora, si comparteixes la pantalla...
No, ara ja està, ara simplement... Com es veu?
Sí, un cremat per la llum.
Malament.
Vol tornar a donar-li a compartir. Que si hi havia alguna altra opció. Si comparteixes directament, fa 7 euros.
Aquí, no?
Però ara que estàs compartint directament això, què passa si pintes? Has d'obrir la finestra a l'esquerra i obrir el llapis. Això es veu ara.
Ara no, no. Que això és només aquí. Pues l'altra opció és amb l'iPad, no? L'altra opció, si no, és compartir-se l'iPad.
Hi ha l'escriptura de l'editor de PDF, està de tot.
En l'Adobe no hi ha
Com s'escriu a l'Adobe?
Vale, heu de tindre la llicència.
No, pots escriure un nom normal. A la pantalla.
Es pot escriure d'alguna manera?
La llicència de la dreta,
Sí.
Exacte.
No, aquest no.
On posa coment.
Rellenar i firmar? No.
Sí, sí.
si està firmat el documental...
Bueno, com a mínim, això és no.
Firmar?
No, però diuen que hi ha una altra opció de
Hi ha una altra opció que és la de comentar, que és...
Per comentar és...
Ah, mira, sí.
Ara sí, molt bé.
Hem de compartir pantalla. És que m'ajuda.
Llavors, espera't, Llavors jo faig així. Per esborrar aquí, no? Bueno, i aleshores per moure'm...
I never tried to get it. I don't like it so much.
Dos dits.
But it does a lot.
I amb això esborro. Amb això pinto. Esborro. Vale, ja està. No compartir pantalla i no hem gravat ara.
Sí, no l'hem aturat de gravar en cap moment, crec.
Ok. I think there is one with the microphone open. Oh, si no. Hello. Okay. So now you can see it well in online. Okay. So I think we can start. Sorry for the delay. Today I decided to do it here because people online told me that the whiteboard was not very clear to see. I will try to follow directly the notes. Okay. Let's see how it works. I always prefer the whiteboard, but let's see. So yesterday we were speaking about convex optimization, continuous optimization, and constraint optimization in the morning. You remember that we have been doing that we have seen the gradient descent method. We have seen the line search also. We have seen the importance of convexity. And today we are going to generalize the problems, but now with constraints. A lot of problems brings constraints. And in machine learning also we have some examples. For example, support vector machine is an example of constraint optimization. Also, constraint optimization appears everywhere in in computational mechanics. So many problems, like a contact problem, you can see it as the displacement you want to be bigger than a value. And so the motivation is that we can find this tool is very useful for many things, not only for machine learning, but also for computational engineering. And so, for example, contact problems, when you want to impose conditions, so the displacement is some value, or that the pressure, for example, for the Stokes problems, or sorry, the divergence of the velocity is equal to 0. This is an inequality constraint in Stokes problems or in Navier-Stokes. So many problems can be formulated this way. So I hope this is a tool that is going to be helpful for you. I wish when I was doing my PhD if I had the time to learn these things, it would be very useful, because today we will learn about Lagrange multipliers, and Lagrange multipliers appears everywhere. My feeling was when I was doing my PhD that Lagrange multipliers were appearing, but we didn't understand, or I didn't understand exactly the meaning and the insight of these variables. And I think it's useful to take the time today in the morning to just try to understand what it is about, and what is more or less what is the insight. What I want to do here today is not to focus a lot on the formulas and the proofs, but just to have an insight of what is about the Lagrange multipliers. Okay. So a minimization problem, we say, a constraint minimization problem, we say that we want to minimize a function f of 0 of theta, subject to some inequality constraints. We will call it f1 of theta. f0 is the cost, f1 is are the constraints. Subject to some equality constraints. Equality we will call it with h. By the way, this book of convex optimization is really good for this part also. Okay, you will see many of these things in that book. So first of all, just to tell you, first thing to say about this is, when we want to minimize a problem with constraints, typically when we want to minimize a problem, yesterday we have seen, what did we do? What were the first order optimality conditions? Who remembers what was the first order optimality conditions for unconstrained optimization problem? Gradient of the function equal to 0. With gradient of the function equal to 0, we have one equation that as many equations as unknowns. Theta is some value, some size, and the gradient has the same size. So we have the same number of equations. With a constraint minimization problem, the first optimality conditions, the number of unknowns were theta, for example, 10. With the gradient equal to 0, we have 10 equations. Okay. So the problem is well posed, you can solve the problem. Now, you want to also minimize a function, but you have more constraints. You will add more constraints to the problem, but you have the same variables, number of variables. So the first intuition is to see that if we do gradient equal to 0, it's not going to work, because we will have 10 equations, but now we have theta, it's 10 equations plus some inequality and inequality constraint, more equations than unknown. So the first insight is to see that it's not going to work, the gradient equal to 0. Okay. So what is happening, in fact, is for each constraint we put or we add to the problem, it appears another variable, which is called the Lagrange multiplier. So this is why I put it just next to the inequality. So this lambda is related with the inequality, and this nu is related with the equality. So we add more variables. With Lagrange multipliers, with constraint optimization, we add more variables. So we have theta and lambda nu are also unknowns of the problem. Okay. For example, in elasticity, you can see if we put here this some Dirichlet conditions, the nu, you can see it as a reactions, as forces that can be computed afterward, but are unknowns of the problem also. So maybe you want to know them, maybe you don't, but they are there always. Sometimes are hidden, but all of them are they are always there. You can compute them, and if you computed them, you have always information, a lot of information that is useful for the problem. So today we will see why these Lagrange multipliers are useful, and the quantity of them, they are also useful. So we first define the Lagrangian, which we will put it L of theta lambda nu, which will be f, so the cost, and also lambda times the inequality constraints plus nu times the equality constraints. We will define it like this. This is the definition of the Lagrangian. What is happening here? Okay. So, and these are called Lagrange multipliers. Sometimes they are also called dual variables, lambda and nu. And theta is a design variable, or also can be is called primal variable. Okay, we will see why are duals and primals. Then we are going to define the dual function, which is a function of lambda and nu, and is defined as the minimum, infimum, or minimum. Infimum is more general because maybe it can be minus infinity. Let's just see it as a minimum of the Lagrangian. So you just define the Lagrangian and then you try to minimize it. This is called the dual function. The dual function, as you see, when you have solved this problem, the infinite value or the minimum value theta, when you plug it here, it does not anymore depend on theta. It will depend only in lambda and nu. This is why we put here g of lambda and nu. Okay, so you give me a value of lambda and nu, and then I minimize this problem. This is how I will compute g. You have to imagine it like this. Give me a value of lambda and nu, then I solve a minimization problem and I take a value of it. Okay, so this is exactly the definition of. This is exactly the definition of the Lagrangian. Okay. Now, first thing about the dual variable, the dual function. The dual function is a lower bound of the primal value. The primal value is the solution of the problem, the minimum value of the problem. You want to minimize, and the dual function is always below this value. So imagine it's you got -1, or so the dual variable will be always below. Okay, this is the first property. Let's see why. So if you take a theta which is feasible, feasible means, remember, feasible means theta fulfills the constraints. So f of theta, fi of theta is smaller than 0, and hi of theta is equal to 0. So the value, the point you have fulfills the constraints. It's not the minimum, but fulfills the constraints. Okay. Then, if we do so, the Lagrangian is the function plus lambda times the constraint. This is the definition, plus the nu times the equality constraint. Since the point is feasible, this value is negative, and this is equal to 0 because it's feasible. Then, if lambda is positive, this quantity here is going to be negative. So 0 plus a negative value, okay, plus a negative value is going to be a negative value. So this is going to be smaller than f0 of theta. Okay, for all theta that is feasible. So if you give me a point that is feasible, then the Lagrangian will be smaller to the cost function for a feasible point. Okay. Then, if we have defined it g, the dual function, as the minimum of this Lagrangian, it means that the minimum of the Lagrangian, of course, will be in the left-hand side of the Lagrangian because it's the minimum one. So this is general, but this one is the minimum. Okay, so the minimum is going to be less or equal than the functional. Okay, this is the definition of the dual function, and in the right-hand side is just what we have before. So the dual function for any functional point that is feasible will be always below the cost with this feasible point. Okay, And now if we take from all the points, this is for any point that is feasible. If we take the one that has minimum value, so the optimal point, we have many points in the domain that are in the convex set. So this is the convex set. Any point of this one, this is theta bar. Then if we take the one that it has minimum value, then of course will be smaller than this quantity because this is for anyone. So you put it here, you take the one that has minimum value. So, and this is called, because it's feasible and it's the one that has minimum value, it means that the dual function will be always below what we call P star, which is the optimal point. Okay. So let's do it again because it's a little tedious. So we take a feasible point. Okay, we take a feasible point. Then if we take a feasible point, we have seen, because if lambda is positive, we have seen that the definition of the Lagrangian is going to be smaller than the function in this feasible point. Okay. Then the definition of the dual is the minimum of this Lagrangian. So we'll put it in the left. So if it's the minimum, it's going to be smaller than the Lagrangian itself. And this inequality is just what we have been doing in the row before. So the dual is going to be smaller than any value, any feasible point. But also we are going to, if it's for any feasible point, we can take it also for the best one. So, and the best one is called theta star. So the dual function is going to be smaller than the optimal point, P star. Okay. Okay. Questions about this? You see, so the dual function, yes.
But what if lambda is negative? That is also.
It's not valid. This reasoning. We will see that in fact lambda we will have to ask for being positive. Yes. So now let's make a plot. So this is a function f of 0, non-convex function, you see. And this is f1, which are the constraints, and you want that the constraints are between these values here. The inequality constraints. You want that this the function is between these values here. Okay. If you plot the Lagrangian, which the Lagrangian, as I was saying, the Lagrangian is the cost plus something else here. In this case, only this part. Then the blue line is the Lagrangian. Okay, we plot here the blue line. So the blue line in the feasible point, and then you have to take the minimum of this function. So you change your function, you modified your function, and you have the Lagrangian. You are adding some terms, okay, which is this blue line. It's not anymore the red one. Okay, this blue line, you have to take the minimum value. This is the definition of the dual function. So the minimum value, for example, for this point is this red. Is this red square? Okay. If for lambda equal to 0.1, if you do it for lambda equal to 0.2, is here, and for lambda equal to 0.3, for example, is here. So you take the minimum value of all the Lagrangians, okay, and you see all of them are below the optimal point, which is this point. This function between this constraint, the optimal value is here, because you see the function, the black one, you have to take the minimum value, and the minimum value is here because it should be in the constraints. So in the interpretation geometrically of the dual function is you modify the function with the Lagrangian, and this is the blue line, and then you take the minimum value, and this minimum value is the definition of the dual function. Okay, all of them, we have proved that all of them are below the optimal point. So these red points are below this red point. These square points are below this dot point. Okay. So as when lambda is going to 0, of course, you will reach the function that you had before, okay, the cost function. You will see that here, so the cost, the dual function, in fact, if you plot it, it's something like this, okay? It's always below P star and depends on lambda. And you see, usually it's concave. It's concave, the dual function always, okay? Okay, this usually takes time to understand this, so maybe you want to explain it again?
Yes, I have a question. Yes. So the red line is originally the cost function without any Lagrangian. Then the blue lines is the cost function with the Lagrangian applied. And or is it just the Lagrangian itself?
So with the Lagrangian is a combination of the cost plus another term, which is lambda times.
Oh, okay. So I got confused. So the term that we're assuming it's not the Lagrangian, but the Lagrangian is itself the summation of the cost function with the term.
Exactly.
And then what is the line or the function that it's on the bottom? Is it?
It's the constraint that you ask to be always smaller than some value. So for example, you want to be you want to be smaller to this value, for example. This is why I put it. So you have to be in between this region. This is the constraint that you put. You put fi of theta is smaller than this number.
Okay.
So the feasible region is here. Okay. So in the feasible region, what we have proven that in the feasible region, the dual function is always below the cost. The optimal point, not the cost, the optimal point, which is this point. Okay. But when you are not in the physical domain, it's not happening anymore. Okay. Okay. Questions? Yes.
What was again the name of the P star?
It's the optimal point or primal point. Optimal primal point. It's the solution of the problem. So it's this point here, the function at this point. Right.
Suppose we don't have inequality constraints. Suppose we have equality constraints.
In this case, no. It's just an example in 1D with a function in 1D also and one constraint in 1D. So no h. Yes, just inequality constraint.
Suppose we have only h. We don't have f. Then
here we have only f. F of I of theta is smaller or equal this value. I don't know which value I put here. I don't know how to take that. Remove this maybe. Yes. So 0. So smaller or equal to 0. This is the constraint I have in this example. And the function f of I is this one. So all the points that are below this line, is the physical domain. So it's here. Okay. So in regions where the constraint is or we have feasible points, then the Lagrangian is always below the function. Okay. In the optimal point. Okay, let's try to understand a little more this idea of dual function and Lagrangian. So usually what we have is we want to minimize f of 0 of theta subject to f of phi of theta smaller or equal than 0 and hi of theta equal to 0. Okay, we can rewrite our problem in a different way. How? This way. We have the cost, so the cost is the same, and we will add what we call indicator functions, which are these deltas, which are functions that takes infinity if the constraint is not fulfilled, and 0 if the constraint is fulfilled. So if the constraint is smaller than 0, the function adds 0. But if the constraint is not smaller than 0, so if we are not feasible, then it's infinity. So you penalize with infinite numbers when you are not feasible, because you want to have, of course, a solution of the problem should be feasible. Always, of course, optimal, the minimum value, but feasible. It should fulfill the constraint. So what you say is, okay, if it's feasible, then I'm going to add 0. If it's unfeasible, I'm going to add an infinity. So they are equivalent problems. These problems here, writing like this, or this form is the same. If a point is feasible, it's going to, we add 0 value. If a point is unfeasible, we will add infinity. Okay, because you want to minimize. So it's like you're not going to solve anything because it's an unfeasible problem. Even if you minimize the cost, it doesn't matter because the constraint is going to be infinity. So you penalize with infinity when you are not feasible. Okay, it's another way of saying it. Now, the Lagrangian is the same of this function. It's very similar to this function, but look, we have the f0 is the same. Yes, f0 is the same. Fi here is also here. Hi is also here. Okay, so it's very similar, but it's always below. Because look, if here there is a mistake, this should be Fi, not H, and here also Fi, not H. Okay, sorry. So if you are in the feasible domain, so feasible domain means here you are smaller than 0, then you add 0, is the green line. If you are unfeasible, here you add infinity. Okay, this is what it means, the indicator function. Or here, when the constraint is 0, then you add 0 value. But if the constraint is, we are looking to the green line. If the constraint is not 0, you add infinity. You see the green line? And we understand this line, okay? But the Lagrangian is something that is below. You see, we penalize when we are a little not when we are not feasible, we penalize in the cost, but not infinity. We do it linearly, and also we like to be as feasible as more feasible than 0. So we penalize also linearly when we are feasible, but with a lot of space, slack. Okay, so we add also linear, so it's not going to be 0. Okay, so the Lagrangian is similar to this function, but it's approximation, a linear approximation, or a linear or hyperplane that lower bound. It's a linear interpolation approximation, so down the real problem. So the Lagrangian is not the real problem, but is like approximation of the indicator function with linear equations. So for example, in this case, if it's going to be 0, you penalize 0, also the same. But if it's a little different from 0, you don't penalize infinity. You penalize linearly. The more you don't fulfill the constraint, the more you penalize the cost. Okay, so the Lagrangian is a different function than the original problem that you want to minimize. It's a function that is going to be below below the original problem. This is the original problem, and the Lagrangian is going to be always below. Why? Because you approximate with functions that are always below the real ones. Okay, so again, another interpretation of this, when we have our problem with constraint optimization, what we want to do is to approximate the function that is discontinuous. 0 is an indicator function. 0 when you are feasible, and infinity you approximate it with linear functions below. Okay, and this is another interpretation of the Lagrangian.
Sorry.
Yes, questions.
Yes, the thing is, I think it's either swapped or mixed. The way that you are calling the Lagrangian.
Yes.
So you call that delta 0. It's the dependence of h.
You're right. Here it's minus, and here it's 0. No. Yes.
Okay.
Thank you.
Yes, to see if I understand it. Then this is how the problem that ideally will be that you penalize infinite when it's wrong, and when not, you put a 0. And then the Lagrange is a linearization of this error, this validation. Then you can derive it, and you can then find the best point.
Exactly. And now
because this type of lines you cannot derive.
Exactly. Okay. Now you have linearity, and you have properties with this linearity. Yes. We'll see it now exactly. And now what we're going to do is, if G, the dual, remember that the dual is the minimum of the Lagrangian, okay, is a lower bound. So let's go up. If we know that for any lambda nu, we have a lower bound of the cost, and we want to find this P star, why don't we maximize this function? Why don't we try to find the best lower bound? If we can find a lower bound that is very close to P, a lower bound can be minus infinity, but this gives you no information. So minus 10 gives more information. And imagine the solution is 0. Minus 10 gives you more information. Minus 5 is more, because you know it's good. So if you want to tell to someone the solution, you say, look, I don't know the solution, but it's going to be above minus 5. This is something also already. So if you start trying to give the best lower bound, it's like trying to find the minimum value. So maximizing the dual is equivalent, and we will see it, to minimize the primal. Okay. So because the dual is something below and is a lower bound, and we want to maximize to exactly attach the primal. Okay. And this is what we call the Lagrange dual problem. Okay. And this is this problem. And now is why we add lambda positive, because if not, it's not going to be a lower bound. So we ask to maximize the cost, the dual, which is a lower bound, with the constraints, because we impose this constraint that lambda is positive. Okay. So this is the dual problem. And dual problem is in a lot of places. So every time you have a primal problem in optimization, you have a dual, always. And sometimes it's useful to maximize the dual instead of minimizing the primal. It depends on how many constraints you have. Okay. And also about differentiability and computational cost, of course. But it's an alternative to maximize the dual. There is plenty of interpretations of this. We can find in many problems. So, for example, in elasticity, you have deformations. If you want to solve it in displacements, then the dual is in stresses. You solve the problem in stress. If you are going to do, I don't know, problems that are having, for example, but it's more in economics. For example, you can interpret lambda in many. For example, the eigenvalues problems. Lambda is the eigenvalue. It's a Lagrange multiplier. The pressure is a Lagrange multiplier of the Stokes problem. In finite elements, you can also find what is the Lagrangian of each problem. So in the constraints, for example, in contact problems, the Lagrangian is the force, the reaction that you have when you impact to the constraint. Okay. So this is what we have. Now we can maximize the lower bound. This lower bound, which is this dual. Okay. let's do an example, familiar example. I hope now we have been using it in machine learning. This is the square problem. Okay, so it's a version of it. It was, remember that before we wanted this to be minimized in L2 norm, and then we added this regularization. You remember this term in the cost. But let's see a version of it that, so instead of imposing the L2 norm to be minimized, we just impose that the constraint is fulfilled. So as a constraint, okay? But it's just to understand what is the dual, okay? Just to see the dual of the least squares problem. So the constraint, the dual is as before. Now we have only equality constraints, so we don't have lambda. We only have nu. So is the infinite, is the definition, the minimum value of the Lagrange multiplier. So it's the infinite value of theta times theta plus nu times the constraint. Okay, this is the definition. This is the constraint. You remember this h of theta. Okay, and this is the cost f0 of theta. Okay. Now you want to minimize this function, so you take the derivatives. Now it's an unconstrained problem. You don't have constraints now. You can use what we have been using in the last course, in the last lesson. So we do the derivative, and we see that the derivative is, this is a square, so 2 times, and this is linear, so x transpose nu. So theta is minus 1/2 x transpose nu. Okay, so we have just solved the, it's a quadratic problem in this case. Yes, you see quadratic, convex, these things we have to see it now. It's quadratic and convex. We take the derivative equal to 0 and we solve the problem. So we have theta equal to this solution, okay? Then what we have to do? With this solution, we have to plug it in the cost to exactly know the dual function. So we take the optimal value and we put it in the Lagrangian. Once we put it here or we add it here, then with some calculations, you will find that you will have this equation here. Okay, this is a lower bound of your problem, of the least square problem. And see, now it does not depend on theta anymore. The primal variable is not anymore here. We only have dual variables. That is why it's called dual variable, because it's in the dual problem. And now we are going to maximize. Why? Because we want to solve the Lagrangian dual problem. We want this lower bound to be maximized. Okay, and this is the problem we have to solve. For example, another application. If you want to solve a linear system of equations with constraints, okay, if you do the duality, in fact, what you have is this functional here, which is the Schur complement for the one that you know, the Schur complement is the Schur complement of the system of equations that you have at the end. So you will see it called in many ways. This is why for me optimization is very useful, because you will see that many problems are called with different names, but in fact are the same things. So duality, for example, is trying when you have a linear system of equations and you have your displacements, and for example you have some constraints. Then if you want to solve just the constraints, you do some substitution and condensation, and then you try to solve the Schur complement. In fact, what you are trying to do is to solve the dual problem. Okay, and what is happening? When is better to solve this original problem? Yesterday we solved this kind of problems. How? For example, we used interior point methods. Okay, or this unconstrained optimization problem. Which is better? Maybe this can be better. How we can decide this? It depends. For example, the number of constraints you have. If you have just few constraints, one constraint, nu will be of one dimension. Maybe theta is 100, but the dual is very small, and the primal is very expensive. It's very expensive. Okay, so sometimes it's useful to solve the dual problem. That is why sometimes Schur complements are useful. Okay, remember, Schur complements are only, this application is only for quadratic equations that has linear constraints, and it's a particular case, but this is general. You can add here any nonlinear function. You can add nonlinear constraint. Okay. So in fact, this maximization of a negative number, you change it, you put a minimization of a without the minus, and you solve the problem with, for example, this with a gradient, or in fact, this has analytical solution. You can just solve the input. Okay. Another example, linear programming. Yesterday we have also this example. So imagine we have in this standard form, we want to solve c theta times ct times theta subject to a theta equal to b with theta positive, for example. If you see theta positive, in fact, you can rewrite it with a minus and write f of I of theta like this. Okay. I don't know if there are questions in the chat. No. Okay.
Can you repeat what was the reason to maximize p in all?
Yes, sure.
Here. What is the reason to maximize?
Yes, because remember we are trying to solve the Lagrange dual problem, which in fact is maximizing the dual. Because the dual is the lower bound of, imagine you have the optimal the problem and you have a lower bound. Then what you want to do is to maximize the lower bound in a way that once you maximize it, you touch exactly the minimum value. And then you solve the same problem, but instead of minimizing, you maximize. And are different problems, are dual problems. Okay. But it's an alternative. Okay. Every time you have a primal problem, you have a dual problem. Sometimes it has different properties. Sometimes the primal is very large and the dual is very small. In this case, sometimes if the matrix is a square, they are of the same size, it's exactly the same. It depends on the problem. Okay. I think this tool, for me at least, is very, very useful because when I read articles or new things, I usually try to see it with these tools. And you can if you have the intuition of these tools, then you can interpret many things with these tools.
So this means that we are solving to maximize the value of the Lagrangian that still solves the same problem, finding the lower bound of the optimal point. So as per se, the problem that you were that you draw before, that as lambda increases, the lower bound of the optimal point was way lower. So we are maximizing that point, but still solving for the. Okay.
You will get the optimal point. Will reach.
Okay.
It's not, and this is sometimes tricky. Not always the dual problem attach the primal. There are some duality gap. Okay, and it's very technical this to understand when you touch the duality gap is 0 or not. I'm not going to give you all the details, but yes, this is the idea. The idea is that this lower bound tries to be maximized. This dual function to be maximized. This is what we call Lagrangian dual, and then you reach the primal, the solution of the primal. Okay. Next example. So the next example is this function is the dual, is the definition. Now remember here. Yes, here I forgot to put lambda, comma lambda, and here also, comma lambda. Okay, probably you will find mistakes in the notes. So the dual function depends on nu and lambda. Yes, sorry, I forgot. And sometimes it's difficult to find the dual variables, nu and lambda. But if you just have some values, if you plug the values there, probably you will be able to most of the times give a lower bound. Maybe not the best one, but a lower one, which is in fact a lot of information sometimes. Okay, just this is another utility of the dual function. Okay, so we define the Lagrangian. Remember the Lagrangian. So the dual function is the minimum of the Lagrangian again, and the Lagrangian is the cost function plus lambda times fi of theta plus nu I hi of theta. Okay, in this case, we have this linear of equations, and here you have this inequality here, -1 only. Okay, this is why you have only theta, -1 times theta is this inequality. Okay. Now you just try to add all the terms that are with theta. So you put it here, and you leave the other ones the other side. Okay. And now, since you want to minimize with theta, these terms is not important, so you can minimize only the second part. Okay. And this problem, since it has no constraints and you want to minimize, if this number is different from 0, the solution of this is minus infinity. Because you give me, for example, imagine it's number 2, then you give me theta minus infinity, and then this is the solution of the problem is minus infinity because you want to minimize. If you take number -2, you take theta infinity, and then the solution is going to be minus infinity. Okay, so I say it again. Imagine you put this and a value 2, then you take theta. You take theta equal to minus infinity, and then minus infinity times 2 is minus infinity, so the solution is minus infinity. If it's -2, then theta, you take it infinity, and then you will get minus infinity. The solution is infinity of theta, and you get minus infinity because you want to minimize. The solution, if you want to minimize, the solution is minus infinity, of course. So if this term here is different from 0, then the solution is minus infinity. But if it's 0, you put it here. This is the solution is 0. So you will only get this term here. Okay. Should I do it again?
We were trying to maximize it to find the
yes. We are going to do it now, but before we define it, the function. Yes. Now we are going to maximize. Yes. Now we are just computing the dual. So this is the function. The function is okay. If this is going to be 0, then you have to solve a linear equation. If it's not 0, minus infinity. Okay, so if you want to maximize this, now you have to maximize this. It's exactly the same as maximizing the cost and asking for this to be 0 as a constraint. Okay, so this is equivalent to maximize this with the constraint this equal to 0. And this is precisely maximizing the dual, but you can rewrite it if you want. Since lambda is any value, you can ask, lambda should be positive, I forgot. So there is another mistake. Okay. And then putting lambda or not, if it's positive, is the same as asking that this is an inequality and you remove lambda from the equation. Okay. Because adding a number that is going to be positive, you say this should be positive, and it's the same. You have one constraint less. Okay. So sometimes linear programming and this minus is with a plus. So changing minus with minimization is maximizing a minus is the same as minimizing without the minus. So sometimes you will find a dual problem of a linear programming like this. So it's also a linear programming, dual linear programming. So linear programming, the dual function is also a linear programming function. Okay, which maybe sometimes will be, as I was saying, easier to solve. If you have a few constraints, okay, nu is going to be very small. Okay, so it depends on what you want to solve. Okay, so we have seen two examples of the dual variables, dual problems, and the dual Lagrangian. So we have the primal and the dual. So minimizing the primal is the same as maximizing the dual, roughly speaking. Let's now see a geometric interpretation of it. So imagine this is 1D problem. 1D problem with one constraint only of inequality and the cost. Okay, so you want to minimize the cost. So you want to be you want to be in the left-hand side. Okay, because you want to be feasible. Then the point of this space where you have minimal point but is in the left-hand side is this point here. And this is the solution of the problem for the primal. You go here and you take the and this is P star. Okay. Now imagine you define the dual as F0 L lambda times F plus F0. Okay. And then you change lambda. Okay. The lambda is giving you the slope. Okay. So, for example, you want to maximize this. You want to move with this slope. You want to move up or down. Okay. So what you are going to do is to given a lambda, you move here. So given a lambda, you move here. You touch the domain, and when it's cutting the line here, so fi equal to 0, then you get the value of the dual function, so g of lambda. Why? Because this is going to be 0, f of I is going to be 0, and you get this value here. Okay. So now the question is, which is the one that gives you the maximum value? Which is the one that you can maximize here the most from all the tangents you have? Okay. So the one that gives you the most is this line here, which is giving you a point here. Okay, so it must be tangent to this. Okay. Yes.
Third one is not a tangent to the.
Yes. No. Yes. Here it's tangent here. Here is tangent here.
This curve is like a Lagrangian.
This is a way to see how the dual. You see here the dual optimal and the primal are not the same. You have a duality gap. Okay, and sometimes it can happen. I plot this example. If it's convex, you will reach exactly the same point. Okay, but if not, you will have sometimes this duality gap. There are some conditions where you can prove that there is zero duality gap, but it's very technical. I don't have time for explaining it. But the important point is the saddle point interpretation, as we were saying, minimizing or maximizing. Okay. Yesterday we were speaking about minimizing is always a convex function when we minimize the gradient is equal to 0. But let's do it. Let's give an interpretation in a saddle point way. So imagine you have the function, this function we had before. You remember in the indicator function. So 0 if it's unconstrained. So if it's feasible are infinity. This problem can be exactly written as this problem, because look, if lambda is, if f of I is negative, okay, and lambda should be positive, the solution of this is taking lambda equal to 0. So you get the solution equal to 0. If f of y of theta is smaller than 0, imagine you want to solve this problem. Okay, if you take lambda, and lambda should be positive, if you take lambda a positive number and this is negative, the one that is going to give you a minimum value is lambda equal to 0. Okay. Okay, so you can rewrite this function as this function here. Okay, now when you have the primal, is the solution of the as before of the cost plus the indicator function. Then I change the indicator function with this formula here. Okay, and then since this does not depend on lambda, I put it before. So I just plug this sub just here because this term you don't see it. So you're gonna do like this. So you have an inf sub problem. Okay. Inf sub max min. So this is why we call it side point. Okay. Now, if the solution of this the dual is also defined as maximizing the Lagrangian, which is the infimum value. This is the definition of the dual problem. So the primal can be written as inf sub, and the dual can be written as sub e min or max min. So one is min max and the other is max min. People who are doing research or in games theories, for example, they have a lot of these max min problems. Okay. So we have that since the dual is going to be smaller than the primal, the sub inf is going to be smaller than inf sub. Okay. Okay. So then the minimum value of the Lagrangian, okay, so this is the optimal one. Okay, so a minimum value of this will be smaller than this, of course. And this one is the optimal one, which is this one. Okay, of course, if this is maximizing, this is the solution, is going to be always bigger than any dual. And if this is the minimization, and if this is the minimization, okay. If this one is the minimization of this one, is going to be smaller. Okay, so this problem is the dual, and this is the primal, and this is any point that is feasible, and this is any point that is feasible in the dual. Okay, so you have this inequality, you have that, and this inequality is important, and we will see it why. What we have now, we have this is any dual, this is any primal feasible, any point that fulfills the constraint. This is the best one, primal, and this is the best dual. Okay? So any dual problem that is feasible, any primal point that is feasible, then the minimum value is here, and then the maximum value of this is here. Okay, so we have these 4 inequalities. Okay, that's what I have been plotting here. So this, and sometimes when you reach P and D, so when the dual and the primal are the same, is as you can say that you exchange max and min. Okay, can be exchanged. Okay. Let's see why this is important. So we have seen that the dual feasible means that provides you a lower bound. Then during optimization, imagine you have an algorithm and you get some values of and you find the optimal values of the Lagrangian multipliers. Then during optimization, you always can check how far are you from the optimal value. Okay? You want to have the primal solution, but imagine you get the dual function during optimization. So you say, how far am I from convergence? Just you see this difference. You see how much is your function or your feasible point, and you write and you compute also the value of the dual, the optimal dual. So of these inequalities that I was saying, these 4 inequalities, you have already the best lower bound, and you have a point that is not the optimal, you don't know, but you know how far you are from the optimal because you have the optimal dual. So the dual can give you information of how far are you from the optimal. So during optimization, you can find this. Okay, this is useful for this also. And let's do now an inequality that is very important. Okay, and this is also a little tedious, but this inequality, if we understand this inequality, then we will understand the Karuskani-Tucker conditions, where are a lot, you will find it everywhere, are very famous. Karuskani-Tucker conditions are the conditions for constraint optimization, are the conditions, for example, for people who are working on plasticity. You have all for sure seen this. The Lagrange multiplier is the plastic Lagrangian. The inequality is where you want that the stresses are below. So are everywhere, the Karuskani-Tucker condition, okay, are very important. But to understand them, we need to understand this inequality. Okay. So let's do it. Imagine we have the optimal point primal, and we have the optimal point, the optimal dual variables. Okay. Now imagine we have zero duality gap. So the optimal primal is the same as the maximal as the optimal of the dual. So the max and the min are the same. Okay. Then by definition, the dual is the infimum of the Lagrangian, and the Lagrangian is this. Remember, the Lagrangian is the cost times this term times this term. Okay. And I have decided to evaluate it in the optimal points. So where I put lambda, I will put lambda star, and where I put nu star, nu, I will put nu star. Since this is an infinity, the minimum value, of course, will be less than the inequality without the infimum. So I write exactly the same. Right? For this. And then this point, this optimal point, is feasible. Theta is feasible, is the optimal point, so it will be feasible. So it means that this term here, if lambda is positive, this term is going to be smaller than 0. So, and this term is going to be 0. So this, all this is going to be smaller than all this, Okay. So we can do it again. This is zero duality gap. Then this is the definition of the dual. Okay. Then the infimum is less than always without the infimum. And here theta star is of course visible. So this is going to be negative, and this is going to be 0. Okay. So in the right hand side of the inequalities and in the left hand side of the equality, we have the same. Okay. So it means that all the inequalities becomes equalities. Okay. And what does it mean? The first thing, if all the inequalities are equalities, means that this equation here, theta star, is the solution of this problem here. Okay. Why? Because this is going to be the same as this. So if this is the optimal point, of course, the best theta is the solution of the Lagrangian. So theta star is going to be the minimum of the Lagrangian for these dual optimal points, of course. Okay. Second consequence is that if this should be equal to this, okay, it means that this should be 0. Okay. Because all are the same, are equality, are not anymore inequality, are equality. So to be this equal to this, since this is 0, this should be 0. Right? Because this now is equal to this. So if this term is 0, it should be exactly 0 because we have seen that all the qualities now, all the inequalities are equalities. And this is the complementary equations or slack equations. You will find it in many places also. For example, in in plasticity, the plastic Lagrange multiplier. You say it should fulfill this equation. Also in contact problems. Okay, so this equation, in fact, we can see it in a different way. How? If lambda is positive, then this should be 0. If one of these is positive, the other one should be 0. And if this one is negative, this one should be 0. When the constraint is 0, the inequality constraint is 0, we say that this constraint is the equality constraint. It's active, sorry, active. The inequality is an active inequality constraint. When the constraint is exactly 0, then the inequality constraint is exactly 0. We say that it is an active inequality constraint, and it's this case. So you reach the border, and then the Lagrange multiplier should be different from 0. It's going to have for example, 2, 10 positive, but different from 0. Okay. And the contrary, if you're not in the constraint, the Lagrange multiplier is going to be 0. If you're not touching the constraint, the inequality constraint, the Lagrange multiplier is going to be 0. Okay. Okay. So let's take all the equations that we have and put it together. And this is what is called Karush-Kaney-Tucker condition. Okay. First, theta should be the minimum of this problem. So let's take the gradient of this problem equal to 0. It's an unconstrained problem. So from this equation, we have to take the gradient of this equation equal to 0. What is this? The first equation. See, before in the unconstrained optimization problem, we have the gradient equal to 0. But now we don't have any more the gradient equal to 0. We have the gradient plus lambda times the gradient of the constraint plus nu times the gradient of the other constraint, the equality constraint, are equal to 0. Before lambda and nu in a constraint problem are 0. So with this equation, it's enough. You can solve it. But now here you have more equations, more constraint, more unknowns than equations. What are the other ones? The other ones are what the problem is asking: to fulfill the inequality constraint, to fulfill the equality constraint, to ask that lambda is positive for the dual, remember? And what we have seen, the complementary equations, which are these ones. Okay, so the Karush-Kaney-Tucker conditions are these equations. Okay, and if you solve them, you find the solution. You have and you have to find theta, lambda, and nu. Okay, so now this is happening exactly the same as when we have an unconstrained optimization problem. When we have an unconstrained optimization problem, we have the optimality conditions. Which was the optimality conditions from the unconstrained? Optimality conditions for unconstrained was gradient of f of theta equal to 0. The optimality conditions for constraint optimization are Karush-Kaney-Tucker conditions. Okay. So it's happening the same for algorithms. It's happening the same as for unconstrained optimization. In unconstrained optimization, we have two possibilities. One, really exactly solving the equation, coming here and trying to find the equation, solving this equation. For example, in the quadratic example, it's solving a linear system of equation. You solve it directly in one step, or you try to find algorithms to really solve this problem. Or the Newton, what was Newton trying to do? Newton was trying to linearize this equation and do and iterate trying to solve this equation. There are other algorithms that are not trying to, the focus is not the optimality condition, it's just descent methods like gradient descent, as we have seen yesterday. So one of them are trying to focus on the optimality conditions, and one of them are trying to focus on descent directions. For example, Newton method is focusing in the optimality conditions for unconstrained problem. The gradient method is focusing on descending. Okay? This is why this is only happening in the optimal point. If you're very far, these equations are not going to be solved, or they are not going to be fulfilled. You will be very far. And expecting, if you're very far, that trying to, with a fixed point method or something, to go to make it zero, sometimes it's not converging, it's difficult. So if you're far, usually what you are using is descending algorithms. And when you're close, you can use fixed point methods that try to solve this Karuskani-Tucker condition. Okay, so algorithms, and we will see it tomorrow. Algorithms that solve Karuskani-Tucker conditions are plenty. You can go here and try to solve a Newton iteration of this. Okay, this inequality you can change it with the slack variables, and you can do some Newton iterations of this. You can use interior point methods also. We will see it. So people are trying to solve this kind of problems directly with Newton equations. Okay, or you can do descending methods. For example, augmented Lagrangian, projected Lagrangians, null space equation problems, algorithms. There are many. Okay, so it depends on what you focus. Okay, typical example, and you will see it many times. Imagine you have a quadratic problem with linear equations, and you have a few linear equations. Then the Karuskani-Tucker conditions have this shape. And probably this is the kind of equation you have seen many times. Here, the quadratic part, the equilibrium, and here sometimes you will have, for example, for the Stokes problem, you will have the divergence, and this is the pressure when it's quadratic. For direct Neumann or Dirichlet or Robin problems, you will have this also as a constraint, and these are the reactions. And so when you have quadratic problems, many problems are quadratic, and the Karuskani-Tucker conditions are this. Just what you have to do is try to, the first equation. The first equation is this equation, this one, and the second equation is this one. Okay, for this example, you have only equality constant, you don't have inequalities. Okay, so if you have problems like this, and see this is symmetric, what you can do is solve this problem directly. Okay, you can inverse this. People can inverse this. You can do it inverse, or you can do substitution, should complement, and this kind of thing. And this asks that A has full rank. Okay, and this is important. For example, for the if sub condition that maybe some of you have seen in finite elements, A sometimes has no full rank, and you have to stabilize. Okay, you have to add something because A has no full rank. Okay, or maybe, for example, why maybe if someone has worked on that, sometimes you see that in the Stokes problem you don't have. You have to stabilize, and you cannot use, for example, the same interpolation from the velocity and the pressure. You have to use less unknowns for the pressure. Why? Because if not A, it's going to be you will add too much constraints. Okay, you will add too much constraints. Okay, and you cannot add too much constraints when you have theta. Okay, which is the displacement. You cannot find a velocity that has too much constraints, because if not, the problem cannot be solved. Okay, this will have no inverse. Okay, A, instead of being a row and a column, will be very larger than K, and this will not be invertible. This is why you have instabilities. Okay, so many problems has flavors of this kind. Okay, and now with this, I think is going to be the last part of the Lagrange multipliers. And this one is the final interpretation and intuition of the Lagrange multipliers. Okay. So let's now try to solve a problem that instead of being the typical problem, the problem that we have, instead of we are going to perturb it and add some small values, u and v. Okay, we are going to perturb the problem with u and v. Okay, these colors should be blue, and this color should be green. Okay, that's another mistake. So the primal, if you give me the optimal point is a point which has minimum f of 0 and also fulfills the constraints fi and the inequality and the equality constraints. Okay. Why is it depending on u and v? It's depending on u and v because you give me a value u and a value v here, and I will have a different optimal problem. If u and v is 0, you have the original problem, the problem you want to solve. But if you perturb a little, you will have a different solution. The solution is going to be different. If you, instead of asking me to be smaller than 0, you ask me to be smaller than -1, the solution is going to be different. If you ask me to be equal to 0, or you ask me to be equal to 1, the solution is going to be different to 0, different. Okay. Only when the problem is 0, so when u and v is 0, you have the original problem. Okay. So you are perturbing the constraints. Then, for any feasible problem, for any feasible point, the optimal point P00, okay, is like you have 0 duality gap, the optimal of the dual. So for definition of the Lagrangian is the minimum, again, is the infimum of the Lagrangian. I remove the infimum, so I can put less or equal. Okay. And then again, since the lambda is positive, this is going to be smaller or equal to this. Okay. So now I substitute fi with u, I, and vi with this. Okay. So for any feasible point, which is this, then P of for any feasible point, which is this, then I pass these terms here to the left. Okay, to here. So I have the left hand side minus this part here. Okay. So this is for any feasible point, but it's also for the best point. So in particular, for the best point, the best feasible point. Which is the best feasible point? The optimal problem, the optimal solution. Remember, when it's feasible and it has minimum value, is the optimal solution. And this is what we call the optimal problem, no? It is the definition of the optimal problem, the infimum, okay, for a feasible point. Okay. So here, instead of putting here, it's going to be particularly for the minimum. This is for all theta feasible, but in particular for the minimum one. In particular for this one, which is in fact for definition this one. So we will have this inequality. It's going to be larger or equal to p star 0, 0 minus lambda I u minus nu times v. Okay, and this is important. This inequality is very important. So if I have my problem and I change a liter with u and v, then, and again, u and v should be in blue and in green, sorry. Then it's going to be larger than these values here. Okay, this inequality. Let's see why is this useful. So if lambda star, the solution of the problem, is large, then the optimal value, again, the colors are not the good ones, will be highly increased when the constraint is tightened. So the problem that we change, if the optimal point is lambda, if the Lagrange multiplier is very large, then if I change a little the inequality constraint, then the optimal solution will increase a lot. The optimal solution, I mean the cost function, will increase a lot. How much? Depending on lambda. And similarly for nu. So if lambda is small, if I perturb a little the constraint, the cost will not see it. So lambda and nu are sensitivities of how much the constraints are tightened or not. If they are very important to the cost, if they are very, very important, if you do a small perturbation, the cost will change a lot. And if they are not very important, the constraints, lambda and nu will be very small. So the numbers you get once you solve the problem, nu and lambda, will give you information of how important are the constraints in your problem. Okay, so for example, for the Stokes problem, if the pressure is 0, it means that adding or not the divergence-free constraint in that point is not important, will not change the problem. But if the pressure is very high, it means that it's very difficult and it changes a lot the problem if you don't impose divergence-free in that point. And similarly, for elasticity, similarly for any problem you will find with Lagrange multipliers, this is with constraints, this is the intuition. So once you see the Lagrange multipliers are always useful as information, you can always compute it. Once you have the primary, you can always compute directly the dual. Okay, so of course people don't use it, but they are very useful to have insight, and also it's very useful also for solving the problem. Okay, so again, if lambda is large, then the optimal value p is highly increased when the constraint is tightened. So you have a large value of u. So the constraint has been changed. If, and the same for nu, if nu is large and positive, when the optimal value is highly increased, then we have it's highly increased when we take v positive. Okay, so it's like having always the same idea of sensitivity of the perturbed problem. So lambda and nu gives you the sensitivity of the constraints with the Lagrangian problem. Okay. Let's also prove it. So you can, for example, do a plot if you want. Also, p of 0 when you don't perturb the problem, you will be here. And then this is u, okay? This is changing the constraint. So this is precisely the Lagrangian, p0 minus lambda star u, okay? And if the problem, if lambda, so lambda is always the slope, okay? If lambda is 0, it's like you have an horizontal line, okay? And it plays no role in the cost. Okay, so the constraint plays no role. You will not change p. Okay. So another way of writing the problem is lambda e star is equal to the derivative of p star times u and the derivative of nu times this is b of I. I'm reading. Sorry for the mistake. The proof. So we have this equation here before, the one, just imagine we take and nu equal to 0. So this is the equation before here. Okay, this one. Then you imagine you take u, you perturb u with a ones and a scalar, okay, and you put it here. You take u like this, so this is going to be 1 times lambda times t on a scalar. Then you pass this to the left and t, you divide it, and then you take limits with positive values or negative values of t, because you can take both. So you have the limit of this difference, of course, the derivative, and then you have positive when it's t positive and negative when t is negative. So in fact, you have equality. Okay, and you can do the same for me. I don't know if I did it here. Okay, no. So to conclude, the value of the Lagrange multiplier measures how tightened a constraint is, or similar, how much the cost will change if the constraint is perturbed. Okay. So to wrap up what we have been doing, we have seen the importance of Lagrange multipliers, lambda and nu. Okay. Then we have seen that we add some new variables. We have theta, and now we have theta, lambda, and nu, because we have more equations. We have seen that the dual problem is always below the primal problem. We have seen that we want to maximize the dual problem to reach the minimum of the primal. We have also taken the Karuskani-Tucker conditions, which are the equivalently primal optimality conditions for the unconstrained problem that is gradient equal to 0. When you think of constraint optimization, you have to say Karuskani-Tucker condition. Okay. And we finally have seen that the Lagrange multiplier has also another interpretation, which is how important are the constraints in the optimization? Are they very important or are they not very important? Okay. So great. I think this is all for today. For now, I think yes. Okay. Yes, perfect. So we can take the break now. You have questions for this?
One question. So when we I think we prove that inequality things is more or less same as equality, but when we derive the KKT conditions, we have the inequality still. That is not clear.
Yes, the inequalities before for the Karuskani-Tucker condition, you mean?
Yeah, because we derived from the Lagrangian and there is no inequality for Lagrangian.
No, but let's go back to the inequalities.
Yeah, here, the second equation.
Yes, this one. This is the primal problem you ask to be feasible always. You need to ask that the constraint, the inequality constraint is fulfilled, and this you ask that the equality constraint is fulfilled. So this your optimization problem. If you collect all the equations you have used, this one is instead at the beginning. So you need to fulfill this to be theta. If it's optimal, it should fulfill the inequality constraint. And if it's optimal, it should fulfill also the equality constraint. And also, which was new, it should fulfill this equation, which is the new one that is replacing the gradient of f equal to 0. This is the new gradient equal to 0 equation, but it's not anymore. Okay, you add more terms and you add more equations.
So, because in the second equation there is an equality, and again we have a complementary slackness condition.
Here.
So,
yes.
So we have to satisfy all. Okay.
Yes. Sometimes it's not easy. Sometimes these equations are difficult. Yes, are sometimes difficult to solve. But there are algorithms for solving this. Sometimes you alternate between prime and dual. So when you try to minimize a little, we will see tomorrow algorithms for solving these problems. But for example, the augmented Lagrangian equation algorithms is trying to solve this problem with a with some ideas. And then you can use Newton for this. For example, you can add some constraints and some more variables and solve a Newton problem, Newton equations. Okay. And there are also projections. You can project in the constraints, so you can minimize and then project, minimize them. There are different algorithms for this. Interior point methods also, that they try to be always inside the constraint, the constraints, so you minimize, and these are always fulfilled. Tomorrow we will see some of the algorithms. Okay, more questions? No, I hope you now understand a little more about the Lagrange multipliers. And I think yesterday when you solved the problem of linear programming, remember in the practice you have solved the linear programming problem, then there you have the primal solution, but you can ask also for the dual. You can ask for the other, and you will see how important are the constraints. So sometimes people don't care about this, but the solution is the primal, but you can ask also for the Lagrange multipliers. So yesterday, for example, the constraint of T, you will see that the Lagrange multipliers for the L infinity norm, one is active and the other are 0. They are not important. Okay. And for the L1 norm, you can see also how are the Lagrange multipliers. Okay. And it's always great to see it because you will see, okay, look, I have this data in machine learning. These points are important, but look, the Lagrange multipliers in these points are larger than these ones. These points are more important than these ones, or are changing a lot more the cost. Okay, so you can also interpret Lagrange multiplier and how important are your data. Okay, okay. So if there is more questions, let's do the break, and then I will continue with the machine learning part.
Recording stopped.
The break is
Already ready.
was ready yesterday.
Let's fix ahí que també va demanar.
You need computer here.